Yar kaşıma. YouTube. Kavşari. Et yapari. Burası tamam. İşte ya. Chat'i açacağız diye anasını satayım. Şurum. iPad'e update mi yapsak ya? Ne?
Şey yaptık tamam. Şimdi biraz iş yaptık şimdi olmadı mı?
İyi var.
E-mail gönderdim. Dokümantasyona baktım. Vensi'ye söyledim. Değişiklikler hazırlayayım. Bir şey sordum çünkü there is something pending. Biraz daha var. O kolay. Onun küçük versiyonu bugün yapacağım.
Helal kız. Tamam anladım, ben sanırım bunun bug'ını niye çalışmıyordu burada. Sesimi de açayım biraz, aynen çok kısık geliyor benim
Açık
sesim.
mı?
Şöyle. Benim sesim böyle. Evet. Ben böyle konuşurken benim sesim biraz daha falanlı filanlı. I. Evet, ben böyle konuşurken sesim çok patlamıyordur diye düşünüyorum. 5 yapalım. Şöyle 1.4 desibel aşağı indirdim pat pot yapmasın diye. Ve tamam, bir gel o zaman sigara içelim. Ondan sonra ben başlayayım. Şimdi. Frame nedir ya? Frame sil ya. Bunları da selam canım, plan nedir? Buraya pinleyin please. Diyorsun. Var ekranda ya. Ya Tombo ahora digo yao yao yao yao yao yao yao bingo. In a container değil. Kendi container içinde wrap'le işte, beni delirtme ya. Group selection ya. Ha ya. Allah Allah ya. Şu da şöyle. Şunu biraz yukarı alsak. Şöyle. Oluyor mu şimdi? Yan yana var mı? Aynen, hepsi yan yana. Şimdi group selection. Buradan da 3 ayrı eğleniyor var. Bu da ayrı ayrı gidiyor eğleniyler. O yüzden 3 ayrı ok çekeceğiz. Bu da aşağıdan çeksek şöyle, aynen. Şöyle. Böyle. Ne yapıyorsun lan? Tamam burası lan. Tamam lan. Oğlum ne yapıyorsun lan? Sana avradını. Kontrol Z yapacaksın ya, bu kadar basit. Niye böyle oluyor bu? Okay. Burada 3 ayrı kablo ile geliyor. Değil mi? Setup böyle şu an. Bir de macchiato var. Ye. Şokomel var. Bir de macchiato var. Ye. Şokomel var. Bir de macchiato var. Ye. Şu Codebase'e bir daha bir bakalım. Şimdi apply volume to audio diye bir map not to gain var. Burada zaten bu while loop'un içerisinde mi yapılıyor, yok. Ama evet, fonksiyon çağrıldığı için burada. Böyle şeyler denemişik. Güzel. En son bu kalsın zaten. Şimdi ne yapabilir? Ne yapabilir? Ne yapabilir? Ne yapabilir? Kapat. Dursun, dursun.
responses and but also alter time domain characteristics. Now, for example, said before, you might want to use this filter to remove high frequency noise, remove a DC offset, or just cut out a certain range of frequencies, or amplify a certain range of frequencies. The question now is, how do we actually design a filter like this? One type of digital filter, and a very common one, is known as the FIR filter. And FIR stands for finite impulse response. A filter in general will have some sort of input denoted by X. We pass it through, in this case, an FIR filter, and we get an output Y. If the input sequence is a 1 followed by all zeros, then what we get out is known as the impulse response, right? We put an impulse in here, and we measure the output. And for an FIR filter, the output will eventually return back to 0. The filter is always stable. And you can see this in this picture here. On the left, we have the input sequence, a 1 followed by all zeros, and the output sequence for this particular filter might look something like this. So it'll eventually go back to 0. And this is why this filter is called finite impulse response. As usual, the FIR filter is a one label, but it's all zeros, or will have some sort of input, one type of digital filter, and a very common impulse response. A filter in general will have some sort of input, denoted by X. We pass it through, in this case, an FIR filter, and we get an output Y. If the input sequence is a 1 followed by all zeros, then what we get out is known as the impulse response, right? We put an impulse in here, and we measure the output. And for an FIR filter, the output will eventually return back to 0. The filter is always stable. And you can see this in this picture here. On the left, we have the input sequence, a 1 followed by all zeros, and the output sequence for this particular filter might look something like this. So it'll eventually go back to 0. And this is why this filter is called finite impulse response. As usual, the FIR filters will be defined by a sequence of numbers of finite length. So again, we have an array, typically denoted by H, which is a discrete set of numbers. And this is what is known as impulse response. And for a linear FIR filter, this is all we need to know about the filter to know everything about it. We know the frequency response characteristics, we know the time response characteristics, and so on. Now, to actually get the output of this filter, we need the impulse response, and we need the input signal. And then we do something which is called convolution. So the output is the input signal convolved with the impulse response. Mathematically, convolution is written like this. So the input signal is X, the impulse response is H, and we typically use this star, which is known as the convolution operator. Now, because we'll be working in discrete time, because we want to implement this on a computer, this convolution actually turns out to be this sum over here. Now, don't worry if you don't understand this or this looks a bit alien to you. I'll show you later when we're actually implementing the software how to do this. But this is a really, really useful and important formula which we'll be using for the software implementation. But this is how we get the output. The output is Y, the impulse response is H, and the input is X. The question now is, how does the impulse...
The output is Y, the impulse response is H, and the input is X. Yani burada P dediğimiz, impulse response dediğimiz buradaki coefficients'lar değil mi?
response is H and the input is X. The question
Bu
now
for
is...
loop'u ya. Bu matematik. Bu sigma for loop'u işte. For C eşittir 0. C is less than m-1. C++. Sonra onun içinde de bunu yapıyorsun işte. Impulse response times input.
The output is Y, the impulse response is H, and the input is X. The question now is, how does the impulse response of this filter determine the frequency of the response of the filter? There are two really important results which I'll leave unproven, but I'll tell you about them now. Firstly, the Fourier transform of the impulse response of the filter is actually equal to the frequency response of the filter. And secondly, we are convolving in the time domain from the formula we saw earlier, and that is actually equivalent to multiplying in the frequency domain. So we have a certain frequency characteristics for the input signal, we have a certain frequency characteristic for the filter, we multiply them in the frequency domain, and that is the same thing as convolving the time domain to get the output. So, quite simply, to design a filter, we need to come up with a desired frequency response. So this could be a low pass, high pass, or any arbitrary form of the frequency domain response. And then we just take the inverse Fourier transform to get the impulse response. In particular, I'm going to show you how to do this using one of the most common methods, and this is called the window sync method. Now, be warned, there's quite a lot of maths in here, so if you're not comfortable with it or you're not interested, feel free to just skip ahead to the software implementation, which I think is probably the most interesting part. So let's look at a simple low-pass filter, which has this frequency response in the frequency domain. So we have magnitude on this axis and frequency on this axis, and we want to pass frequencies below a certain cutoff frequency, known as FC, with a magnitude of 1, and above that cutoff frequency, we don't want to pass any frequencies. And this is a very, or the ideal low-pass filter. Now, as I said before, we need to take the inverse Fourier transform to get the impulse response. The integral in continuous time is this one here, and then we just plug in all the values. Remember, we're only integrating from minus fc to plus fc because all the other values outside that range are 0, and then we just do the integral. Now, it happens to be that if we solve that integral,
Hoş geldin
the
reis.
impulse response in continuous time, remember, is sine divided by pi t. And this is actually known as the sinc function. So here you actually see where part of the name comes from for this method. Now the sinc function, if we plot it or do a little sketch, it's this one here. Unfortunately, this brings quite a few problems with it. Here again is the theoretical response, the impulse response of our low-pass filter. Now we can see several problems. One of them
You
is
look like my
non-causal.
kind of stream,
So
bro,
for
bro.
time values below 0, we actually have
Eyvallah, bro.
non-zero impulse response values, and we can't implement that. We also have infinite length. So even though these tails decay towards 0 as t goes to plus minus infinity, they will still be non-zero. So it has infinite length. And thirdly, because we want to implement this on a computer, it's in continuous time, and we need discrete time. But of course, we have a solution for all
Şimdi
of
bir
these.
göster
The
bakayım
first
bana
one
bu
is to
nasıl
shift the
yapılıyor.
response to the right.
Choices
Then we want to
menfi.
truncate.
Ha,
We want to chop
şunu,
the
şunu
frequency
anlat
response.
bakayım bir de.
Now we will have many different choices when designing FIR filters. Firstly, we need to think of the sampling frequency. And this is oftentimes governed by the system we're going to be implementing this on. But ideally, if we could choose, we want to sample as fast as we can, because then we're not limited by a really low Nyquist frequency and so on.
44.1, bro.
So a longer filter, a longer impulse response will give us a more resolution in the frequency domain. Then of course we can define the frequency response in the filter type. So do you want a low pass, high pass, band pass, notch filter, and so on. The windowing function is quite important.
We
to
want
choose,
band
there's
pass.
Stuff like Hamming,
We want
Ham,
low, mid, and
Hamming,
high, bro.
Blackman, and so on. Lots of different windowing functions we can choose from, and they all have different benefits in the time and frequency domain. But we're not only interested in the frequency response of a filter. Sometimes signals of interest, our input signals, have really sensitive time domain information, and we don't want to distort that too much. So we might want to look at things such as rise time and overshoot and so on. So I've written a little program in C# that'll actually help you design different types of FIR filters. And you can find this in my Git repository under the Hades.
Blizzard'dan ne indiriyorsun lan aynı anda bunu? Blizzard'dan Overwatch'ı indiriyor bunu yap.
And also the C code for implementation and a bit of raw sensor data for you to test it out on. So we can actually use this to visualize the filter responses in the time domain. In the frequency domain, we can look at the window function frequency response and the window function time domain response. And you have all these different parameters down here that you can play with. For example, the sampling frequency, the filter length, how many samples we should shift the filter, and kind of for different filter types, low pass, high pass, band pass, and band stop. We can plot the impulse and step response, and so on. And we can also choose the window function. So I really do suggest that you play around with this, because it's quite cool to see how different windowing functions have different effects on the filter responses. So we can play around with that here. Always click on design filter, and you can see that might have better stop band attenuation, less passband ripple, and so on. Yeah, so I strongly just encourage you to have a little play around with that, you know.
Okay.
And it's quite good to see and get a kind of intuitive feel of what all of these parameters do and change. Another website I can recommend is this T-filter, and this is basically an online FIR filter designer. You can specify your sampling frequency, the filter length you want, and you can kind of just add pass bands, stop bands, so you can make pretty arbitrary frequency responses for your filters. So we can use that, or use the tool I wrote to generate time domain coefficients, filter coefficients, and so on. But okay, let's move over to actually implementing one of these filters. Before we can get started...
Bir de chat'e bir şey soralım. Bir de ondan önce şu dokları... Doklar lazım olunca açarız ya. Chat'e bir şey soracağım. Create image'i getirmişler Foro'ya. Nasıl modelleriniz var amca şimdi sizin? Model dağarcığı değişmiş. Great at coding and visual reasoning. Let's try this guy. How can I design la ana elim F'de buraya gidiyor lan, dur. Benim biraz el bozulmuş. Biraz eli düzeltmek lazım. How can I design a filter for high, mid and low bands to pass. La. To split a signal into low, mid and high frequency bands, you simply design 3 FIR filters. Low pass with cutoff at F1, band pass between F1 and F2, high pass with cutoff at F2. Okay. Below is a work-through recipe. Specify your requirements. Low pass sıfırdan F1'e, pass band, stop band, ripple. Sıfırla F1 arası. Pass band için sıfırla F1 arasını passliyor. F1 artı delta F, Fs bölü 2'yi de kesiyor. Band pass that shit F1 minus bla bla, tamam. Your sampling rate. Hayır, bizimki 44.1. Your band edges 100 Hz, 2 kHz. Tamam. Yani bu F1, F2 dediği şey ne biliyor musun? Şu. Hemen gösteriyorum. Neydi lan? EQ8. Bunu kapa. Kalmasın buradan. Bak, o F1 dediği şu. Bu 2'ye F1 diyeceğiz mesela. Bu bizim F1'ımız olacak. F2 dediği de şu. Bu da bizim F2'muz olacak. Böyle. Ve bunları bu knoblarla kontrol edecek. Şu knoblarla. Yani bundan 3 tane olacak. 1, 2, 3 tane. Bu dördüncüsü olmayacak. Bu 3 tane olacak. Her biri cutoff'lu olacak. Yani band pass'li. Yani low cut mesela. Daha steep yapalım bunu. Daha keskin olsun. Kessin böyle. Tamam mı? Dur bakayım. Yok lan, band pass yapıyoruz. Şunun şöyle olması gerekiyor değil mi? Tabii. Böyle olacak. Frekansın. Tam bu frekans. Q. Bu Q ne acaba? Bak, bu Q'yu nasıl ayarlayacağız bilmiyorum. Yani F1, F2, bu 1, 2 tane, 3 tane olacak. Bunlar böyle ayarlanabilir olacak. Böyle. Bu da olmayacak. Şunu kapa. İyi. Böyle bir şey işte. 3 tane olacak. Bunu 3 tane atacağız. Ben bunu mesela sola çevirdiğimde böyle olacak. Sağa çevirdiğimde böyle olacak gibi. Baksana şeye ne oldu? Sinyale bak. Sinyalle oynayayım mı biraz? Oynadık sinyalimizle. Tamam, devam ki. Tamam. Okay my boy. Transition with you can afford. Delta F transition with you can afford. Q dediğimiz şey delta F mi lan? Transition with. Anaya joyik. Anaya banaya joyik. From your ripple attenuation specs and transition with, you can estimate the required number of taps and via the Kaiser formula. Şimdi tap ne demek burada? Where A in decibels is your stop band attenuation. Şimdi ben bir kere bunun anlamını bilmiyorum. Attenuazione. Zayıflama. Aşağı indirecek yani. Tamam. Stop band attenuation. Dur bakayım şimdi bir daha girelim. From your ripple. Ripple ne peki? Ripple'da çıkarma. Ha, ripple yükseltme, attenuation düşürme mi oluyor? Ripple dalgalanma. Dalgıcık. Şu kübik. Specs and transition width, you can estimate the required number of taps. Number of taps ne? Where A in decibel is your stop band attenuation. Round up to the next odd integer. Compute coefficients. Offline. Aynen bizim coefficient'lar bak şimdi. Şurada coefficient'ları bize Cloud çıkardı biraz. Şurada biraz coefficient'larımız var falan filanla. Şimdi onları deneyelim o zaman. O coefficient inter'leri deneyeceğiz. Değil mi? FIR filtering in C. Şöyle bir göster bakayım neler yapmışsın sen. Here is a sepela direkete formu. Şu şeyi kapatalım ya. Bunu şu an görmemize gerek yok. Ctrl W. Ctrl W. Alt W. Evet. I love end tabs. FIR filter order demiş burada ona. Burada end tabs diyor. End tabs FIR filter order'ına ne demiş? 31. Filter order. Number of coefficients minus 1. Al ha. A filter order. Place with your actual coefs from Python MATLAB. Tamam evet. Buraya şeyler geliyor. Şu coefficient. Coefficient değişken. Neydi lan coefficient? Coefficient. Katsayı. Katsayı. Goddamn. Katsayılar bunlar yani. Type abstract. FIR filter demiş. Buff. Ntabs IDX. IDX ne? FIR init force. Process one sample through filter age. Filter goddamn. Example usage FIR filter low, filter mid, filter high. Ay. Form convolution. For large N, consider FFT based or polypace implementation. Değil. Audio boyumuza gelelim. O kanat mı yok ki? Şimdi bizim audio boyumuza son dosyalarımızı atalım. Ha şeyi açmayı unuttuk lan. Ben diyorum bir şey unuttuk da neyi unuttuk. Şunu açalım ya. Arkadaşı açalım. Arkadaş bize lazımdır. Yes sir. Yes sir. Sola gelir misin? Heh, teşekkür ederim. Here's the reality based on the project setup. Line code completion, alt shift code generator. De buraya soracağım. Bakalım ne diyecek. 3.7 sonet. Oo! Oo! Topluyor reis, topluyor. Nice. Can greatly speed up FIR filtering. Tamam, o zaman şey yaparız ya. Kendi filtremizle. Önce kendi filtremizle deneriz. Sonra Fmac deneriz. Tamam. Ekranda ne yazıyor şu an? FIR filtrelere bak. Buradan koduğumuza geri dönelim. FIR filtreleri uygula diyeceğim. Yeah. FMAC versus manual filters implementation. Dur şimdi. Dışımdan okuyacağım. Understanding your hardware. Your project is using STM to be FMAC is already initialized in your code. Evet. Recommendation. I recommend a hybrid approach. Start with manual filter implementation for these reasons. Gain a deeper understanding of the filter characteristics and behavior. Okay, that is my goal actually. Debug and tune the filter parameters more easily. Have more control over the implementation. Establish a baseline for performance. Then transition to FMAC for these advantages. Significantly better performance. FMAC can process filters with minimal CPU overhead. Lower power consumption. Yeah, that's cool. Free up CPU time for other tasks. Implementation strategy. Phase 1. Manual filter design. Roger, roger. Benefits. Let's start with manual implementation then. What should we do first? Dedim. Rolani almıyor lan. Okay. Okay, that's cool. God damn. That's cool, tamam. Peki ben bunu yank yapınca buraya pes diyecek mi ki o? Yo, yapmadı. O zaman öyle. Bu ne demiş? Tamam. It's much easier quickly validate your filter. Tamam. Therefore I start first manual design and test the filter software. Then after. Allah Allah. İkisi de aynı şeyi önerdi. Tamam. Hadi bakalım. Would you like me to suggest a simple C function you could use to manually apply a second order biquad IRR filter to your ADC buffer as a starting point? Bro, what? Then you can you could add 3 biquads. One for low, one for mid, one for high. Couldn't we use FIR instead of IRR? IIR. Al bunu reis. Sen de bunu al. Hadi bakalım. Define filter types and structures. First order IIR. Aa bak bu da IRR'lı yaptı. You're thinking carefully. Good. Okay. Will we use FIR? Bak nasıl kanıma giriyor şerefsiz chat, görüyor musun? Kanıma girmeye çalışıyor. Should we use FIR or IRR for a manual 3-band EQ? FIR filters finite impulse response. Always stable, no feedback. Easy to design linear phase filters, no phase distortion. But higher computational cost for sharp transitions, many taps needed. Taps dediği burada geldik yani. Taps dediği bu şey herhalde. Her şu yukarıda array vardı ya. Her farklı numaralar vardı. Onların her biri tap herhalde. Many taps needed. IRR filters, infinite impulse response, very efficient, much fewer multiplications needed for similar sharpness. Easy to get second order band pass, low pass, high pass. But they can have phase distortion and require stability checking. This is why I want to use FIR, bro. For a basic real-time 3-band EQ, IRR is the better starting point. You can easily design bi-quad filters, second order sections, much fewer CPU cycles. Later, if you want hi-fi EQ with zero phase distortion, you can consider FIR. But for now, IRR is smarter. Allah Allah. Okay. Sen ne diyorsun peki bu işe? Cloud'e. Cloud'u. Let's start with a manual implementation of digital filters of your user. Define filters types and select first. Let's direkt design'a geçmiş. Alpha preview'un first order IRR, filter type, tek bir yer içerisinden low, high ya da band pass olarak seçiyorsun. First order IRR, filter type, filter coefficient. Alfa'ya filter, filter coefficient, tamam. Ona alfa demiş. Previous input sample, previous output sample. First order IRR. Second order IRR, biquad. Denominator coefficients, numerator coefficients, previous input sample, biquad filter. Now create the implementation. First order filterini, first order filter process. Şimdi ne yapıyor? Alıyor onları. Type'ı type yapıyor. Filter'ımızı. Filter'ı setliyor high, mid, low diye. Nedir? Ne alacak? Alpha equals dt over rc plus dt over dt 1 over sample rate. Is 1 over sample rate. Sample rate'imiz belli bizim ya. 44.01. 44.101 değil. Uydurayım. Prepares. Evet, şimdi what the hell is a bi-quad filter? What is bi-quad filter? Hmm. Intéressant. Le magnifique. Ha, şurada bir
Writing
bakalım.
actual code, we need to remind ourselves of what it actually is we need to implement. And in particular, the most important part of an FIR filter calculation is this convolution sum we have here. Now, again, it looks a bit daunting, but we can actually break it up down here. So essentially all we want to do is compute the output, and we do that by convolving the impulse response with the input signal. And the impulse response is here, and we kind of shift the input signal via this formula. Now we can write this out and expand this sum, and maybe this looks a bit more appealing. And if you just look at this for a second and then just compare, then you can see that it actually isn't too hard. Here we can see that the impulse response goes from 0, 1, 2, 3, and so on to the length of the impulse response. But the more difficult part is actually that we have this input buffer, which changes all the time as we get new input samples, and we have to shift that. So we start with the first one, then we shift it by 1, shifted by 2, and we shift it essentially by the length of the impulse response. And this gets actually quite hard to do efficiently. The question is, how do we actually do this efficiently in code? Because this can really slow us down and make our filters really short or not work at all. So if we go the traditional method of just using normal linear arrays, I'll call them buffers from now on, the problem is we need to shift the input samples all the time, right? So let's say we start out with this array, we have a length 4 input buffer, we have 4 samples, we get a new sample, x of n plus 1, we need to move 3 of these, discard the last one, and put the new input sample at first place. So you can see here we need to make the jump from this to the jump here. We've shifted 3 samples and we've added in the new one. And as you can see, we spend a lot of time just shifting samples, and that's time wasted. So let's see if we can think of something better. The solution, and oftentimes in the DSP you will find this, is a circular buffer. Effectively it's like a normal buffer, except we're keeping track with a pointer to the oldest sample. So let's say we have our length 4 array here, we have xn, xn minus 1, xn minus 2, xn minus 3. xn minus 3 is our oldest sample, and that's the one we want to replace as soon as we get a new input sample. And we also have a point that keeps track, so it'll point to the oldest sample. When we got a new sample, we put it in the array where the pointer was pointing to, and then we update the pointer. I'd suggest looking at this article, and I'll leave the link in the description, and this goes into far greater detail about circular buffers and their uses in digital signal processing. And I think it's a good read and explains the difference between linear buffering and circular buffering and why it's so useful. But let's get on with coding.
I want to read that. Where is that shit? Yes. Let's go. Let's go. Ya dur. Dur. Biraz burayı göster. Şimdi göster bakayım nasıl görünüyor. Güzel görünüyor mu okumalık falan? Tamam, güzel görünüyor. Tamamdır. This article discusses circular buffering, which allows us to significantly accelerate the data transfer in a real-time system. Okay, let's read this bad boy. Allaboutcircuits.com. I want to join this bad boy. I want to join this and I want to get emails about new stuff. Should I do it here? Let's do it like this. Şöyle yapalım. Kardeş. Şuna da basarsın artık be ha. Alt Shift 2. Bu chat nerede? Bu chat kapalı olmadı. Evet. Arayı sallayırım. Şuna bir kaydolacağım. Sign in with GitHub varmış burada. Boşuna yaptık ya. GitHub'ımla girerim ben buna ya. Bas bas reis bas. Shift 3. Ve geri aldık. Mail de geldi. Neymiş bu şimdi? Username required. BCA desek olur mu? Brom. Occupation. Firmware engineer. Embedded. Do you have embedded, my boy? If you don't have embedded, we can go with firmware engineer. Company name. No. Product interests. Embedded software. Embedded. PCBs, power, sensors, test, measurement, wireless, memory. Development boards. Yeah. Electromagnetic. Tamam. Application. Audio. IoT, DSP. Yeah, that's all good. Company. I don't want to give you my company's name, my boy. Usernames must be unique. Tamam da. Göster burada o zaman. Biri almış mı almamış mı diye. Allah Allah. Hadi bunu da almış olsunlar da göster bana bakayım. Yeah, we know that. Confirm. Tamam. Confirm'ü çaktık. We are always looking for engineers who are interested in writing news, projects and technical articles. To find out more, please visit network of published engineers. Okay, that's cool. Why not? You can do that. Circuits. Okay, we got it. Let's go. Circular buffer, a critical element of digital signal processing. So this is 2017. This article discusses circular buffering, which allows us to significantly accelerate the data transfer in a real-time system. This article discusses circular Niye iki kere? Okay. A digital signal processor is a specialized for kind of algorithm. Main goal is to accelerate the calculations while keeping the power consumption as low as possible. In this article, we review a basic addressing capability of this DSP processor, circular buffering, which allows us to safely accelerate the data transfer in a real-time system. Tamam. Please note that since the acronym DSP stands for both digital signal processing and digital signal processor, we will use the term DSP for processor when referring to the hardware rather than the algorithm. Güzel. Since the finite impulse response FIR filtering is a common operation in DSP, we will continue our discussion based on examining the difference equation of an FIR filter. This example will show the typical properties of many DSP algorithms. After reviewing the problem of handling the incoming samples, we will discuss the circle buffering as an efficient solution to the problem. Tamam. Şimdi buna diye bakacağız diye. Vay efendim diye. Assume that we have a 4-tap filter with the following difference equation. 4-tap. Bu tap dediği şey lan. Bunlar tap dediği. 1, 2, 3. 4 tap deyince 4'üncü de açık oluyor. Okay. BOX B0, B1, B2, B3. Aynen. 4 tane nokta var equalizer üzerinde. Tamam mı? Assume that we have a 4-tap filter with the following difference equation, where B0, B1 to B3 are the filter coefficients. And Xn denotes the input samples. Calculate equation 1. We need to store the last 4 samples of the input in a memory. Okay. Yani yukarıdaki denklemi çözebilmek için 4 tane son 4 sample'ı alıp memory'e koyuyoruz. Assume that we have a real-time system such as a hearing aid. Tamam. I don't assume we have a real-time system here. Yeah. In this case, there is an infinite number of input samples which become available to us over time. As a result, we may take one input sample, calculate equation 1, equation, move the result to an output device, and then repeat this procedure for the next input sample. Hence, this example requires the following steps for each input sample. Yani diyor ki, sen değil. Şimdi sonuçta bu gelen datanın geldiğini belirleyen şey zaman aralığı. Bu zaman aralığı sonuç şeyinde şey diyoruz. Dur toparlayamadım lan. Bu denklemde bir tane, yani bu gelen şimdi input datamızdan bir tane sample alıyoruz. Tamam mı? Sonra bunu bu equation'da uyguluyoruz. Ondan sonra da çıkarıyoruz. Buraya çıkarıyoruz. Tamam. Acquire an input sample from the analog world and find its digital representation using an analog to digital converter. Acquire an input sample from the analog world. Yani ses yayıyor bize efendim. And find its digital representation using an analog to digital converter. Tamam. Bak. Buradan sinyalimiz geliyor. Böyle fıçı fıçı yapıyor. Giriyor ADC'mize. Inform the system that the new sample is available. Store the new sample in the memory. In the example of equation 1, we will need this new sample to produce 4 output samples. So we have to store the acquired samples for some time. Use the new sample and the last 3 samples to calculate equation 1. Move the result to an output device, such as a dock, or simply store it somewhere in the memory for later use. Tamam. Really nice. This example shows that a simple DSP algorithm involves data transfer, inequality evaluation, and a lot of math operations. A simple DSP algorithm involves data transfer, inequality evaluation, and a lot of math operations. For example, during step 3 and 5, we have to transfer respectively the input and the result to a memory location. Step 4 involves a lot of math operations. Ha, ben bunu görmüyorum değil mi, stepleri şu anda? Yo. Yazmıyor ki stepler. Ah gözüm. Flash attım. Step 4 involves all the math. The input samples are multiplied by their corresponding filter coefficients and the products are added together. The input samples are multiplied by their corresponding filter coefficients and the products are added together. Okay. Yani aldığımız input datasını oluşturduğumuz coefficient buffer'ıyla falanlayıp filanlıyoruz. Bunları çarpıyoruz. Ekliyoruz. Sonra gönderiyoruz. This is generally achieved by a dedicated multiply and accumulate unit. Multiplier accumulator. Ha bak, bu ikisini, bu gelen input, bu da coefficient'ımız. Yani şu input, şu coefficient geldi, çarptın, multiply and accumulate unit. Mac. Bizde Mac var mı? Kordik var bizde, kordik. Kordik be canım, kordik be. Utilities. Middleware and self-whale. Layer. Bu da tamam. BSP. I have no idea what the hell is that, boy. Security. Multimedia. Connectivity. Yok ya, computing'de vardır, varsa o da bizde yok der. Tamam. The simplify model of a Mac. Step 4 requires some inequality evaluations to keep track of the intermediate results and control the loops. Tamam. Yani diyor ki ortanca değerleri kontrol loop içinde, iç üstünü kontrolde tutuyor. Bak. Evet. İşte böyle oldu. The math operations in step 4 seem to be the most time-consuming part of the algorithm, and the DSP processors attempt to accelerate these calculations using various techniques. However, it is interesting to note that without a careful... Dur. However, it is interesting to note that without a careful design, operations such as transferring the data and controlling the loops can be time-consuming too. In the rest of this article, we'll review A well-known technique, circular buffering, to facilitate the data transfer in a real-time system. Linear buffering. The direct form realization of equation 1 is shown in figure 2. The direct form realization. Bu şey yani. Formülün buraya dökülmüş hali şu anda. Z B0 düz geliyor. B1 B2 bunlar hepsi toplanıyor, accumulate ediliyor. The direct form realization of a 4-tab filter. 1, 2, 3, 4. The above figure suggests that we need 4 memory locations to store the current sample and the 3 previous samples. When a new sample is acquired, we will discard the oldest sample and push the other samples upward by 1 memory location. Allah Allah. Yüklüyor da. A linear buffer at A time index N3 and B and 4. Figure 3 A shows that time index N equals 3, yani 2004. The last 4 samples stored in the memory are x3, x2, x1 and x0. When a new sample is acquired at N4, the last 4 samples x4, 3, 2, 1 and will be stored in the memory as shown in figure 3b. Yeni data geldi mi? Aynen. Linear şey neydi? Linear buffering. Biz bunun circular buffering'ini yapacağız. We'll store shown in the figure 3b. This approach to storing the incoming samples is called the linear buffering. As we will see in a minute, it is simple but not at all efficient. The main problem with linear buffering is the amount of the data transferred that we need to handle. Consider the above linear buffer for the 4-tab FIR filter. With each new sample, we have to read 3 memory locations and write their contents to another location in our array. This is shown figure 4. This is shown in figure 4. Aynen. Buraya yeni data gelebilmesi için en sona 2004'e yeni data gelebilmesi için bir önceki 3 datanın memory adresi okunması lazım ve shiftlenmesi lazım. With each new sample, we have to read 3 memory locations and write their contents to another location in our array. This is shown in figure 4. We observe that the number of the read and write operations are proportional to the length of the filter. That's why the linear buffering is not an efficient method of storing the incoming samples. Yani burada sadece 4 tane coefficient'ım var. O coefficient'ların biraz önce kaç tane olduğunu gördük şeyde. Çok fazla olunca her biri için bir shift operasyonu gerekiyor. It's too much, no. That's why the linear. For example, if we use a linear buffer to implement a 256 tab filter, then with each new sample acquired, we have to perform almost 256 read and write operations. God damn, but too much. I actually did that, and I want to do that. Let's go. We can remove that later if you don't like it. Decline. Circular buffering. Let's examine. Figure 3. one more time. Roger that. The memory in figure 3a stores 4 input samples, x0 to 3. Figure 3b stores x1 to x4, along with the new sample x4. We observe that 3 values, x3 to 1, are common between the 2 cases shown in figure 3. However, different memory locations are used to store these common values. Can we use the above observation to reduce the number of required read and write operations? We can. For example, what's the point of copying x3 from the hypothetical memory location 2004 in figure 3a to the address 2003 in figure 3b, and then using it in the upcoming calculations? If we keep the common values where they currently reside, then we only need to store the new sample. Yani niye shiftlememiz gerekiyor ki zaten? Ha, tepeye koy diyor. Şöyle aşağı koyup shiftleme diyor. Tepeye koy diyor. Hendi ne yapacaksın hepsini shiftleyip diye. Are common between the two cases shown. Tamam. Nerede kaldım lan? Dur. We keep the common values where they currently reside. Then we only need to store them in the memory. When x4 is required, we no longer need x0. Oh yeah, that's true. So we can overwrite it. Hence, we can use the memory location 2001 to store x4. The result is shown in figure 5. Okay, the oldest sample, the newest sample. Okay, but this kills. Like, this is not a. Then this becomes circular buffer, right? We'll see. As shown in this figure, the newest sample x4 replaces the oldest sample. Evet. In this technique, for storing the incoming samples is called the circular buffering. In this way, with each new sample, only a single memory write operation is required. Nasıl yani? Head tail'ı nerede bunun şimdi? Head tail aynı yerde mi? Dur şimdi. Circular buffer at A time, index N3, B and 4. Figure 6 shows how the next 4 samples will be placed in the circular buffer of this example. Göster bakalım. Aynen. Head tail. Head dediği newest, tail dediği oldest. A, B, C, D. Bak şimdi. Nasıl? Önce 4 geldi. En üstteydi. Oldest da onun bir altındaydı. Tamam mı? Şurası. Şu newest oldest bir üstteydi. Şurası da 1'di değil mi? Bir aşağı indik. Yenisi geldi. Yenisi buraya girdi. Artık en eskimize gerek kalmadı. Artık en eskimiz bu. Yani head ve tail'ı takip ediyoruz. Güzel. Bak şimdi gene aşağı geldi. 5, 6. Şimdi bak. Yani bunu yuvarlak şekilde hayal ederse şu oldest'ın diğer tarafa atlaması daha mantıklı oluyor. O yüzden circular buffer deniyor. Bu reis buradan anlatmış bize bak. Aynen circular buffer dediğimiz şey bu işte. 2004'ten 2001'e geçiyor ya. Şöyle dönüyor sadece burada böyle. Head tail birbirini kovalıyor. Newest bu oldu, oldest bu oldu. Dur şimdi. 2004 newest, 2001 oldest. 2001 newest oldu. 2004 oldest oldu, evet. Yo. Nasıl ya? 5 oldus'un 5'e gitmesi gerekiyor. Figure 6 shows the next four samples will be placed in a circular buffer of this example. Based on the above discussion, each new sample replaces the oldest sample. Please note that the position of the newest sample in each state figure 6 ne? Please note that the position of the newest sample in each state of figure 6. With each new sample acquired the position of the newest sample moves forward by one memory location from figure 6 to figure 6A to C. What? Each new sample acquired. The position of the newest sample moves forward by one memory location from figure 6A to figure 6C. Body what? However, when the new sample position reaches the end of the buffer, figure 6C, it jumps back to the beginning of the allocated memory. We can think of this as a hypothetical circular memory where the end of the buffer is connected to its beginning. Figure 7. When we reach the end the buffer, the next memory location will be the first location of the buffer. This explains the name chosen for this technique, the circular buffering. Nasıl ya? Bu typo mu ya? A'dan nasıl C'ye geçiyor, ben onu anlayamadım ki. Beşten sonra 6 geliyor işte. A, B, C diye gitmiyor mu? Neyse. A pointer to interpret the content of the circular buffer. With the linear buffering, each memory location corresponds to a particular time shift relative to the current sample. With the linear buffering, each memory location corresponds to a particular time shift relative to the current sample. This doesn't change with the time index at which we are examining the memory. For example, the memory location 2004 corresponds to the current input sample of both figure 6, figure 3A and B. That's why in figure 4 we can name the memory location 2004 as XN. The memory location 2000 as XN and so on. With the circular buffering, this is not the case. For example, in figure 5A, the new sample resides at memory location 2004. However, in figure 5B, the new sample is at address at 2001. For example, in figure 5A, this new sample resides at memory location 2000. However, hence, while the circular buffer contains all the required samples of the input to perform the FIR filtering, we have to determine the time shift associated with each memory location at a given time index. This can be easily achieved by defining a pointer to the location of the newest sample. A pointer is a variable whose value is an address. For example, to recognize the newest sample of the array in figure 6A array, we need to set the value of the pointer to 2002 as we require a new sample in figure 6b. The pointer value will increase by 1 to point to the memory location 2003 and so on. Obviously, due to the circular behavior of the buffer, the pointer must jump back to the beginning of the buffer when the pointer reaches the last memory location. Hence, in addition to a pointer to the newest sample of the array, we should also be able to recognize the first and the last location of the buffer. To this end, we can use two other pointers to store the address of the first and the last memory locations. Alternatively, we can use a pointer to store the first memory location and a variable to store the line. When implementing a real-time system, we find a circular buffer critical whether we are using a DSP processor or a general purpose processor. However, with GPP, we may have to implement the circular buffer in software. As discussed in the previous section, with each new sample, we have to update the pointer which contains the address of the newest sample. With a circular buffer implemented in software, the programmer needs to With a circular buffer implemented in software, the programmer needs to take care of updating the buffer pointers after each read and write operation. When the pointer reaches the end of the buffer, the program must wrap the pointer back to the beginning of the buffer. In a demanding application, we may not have time to continuously check the pointers to see if they have reached the end of the buffer and wrap them back to the beginning of the buffer when necessary. As a result, a DSP processor uses dedicated hardware to provide some fast circular buffers. This hardware implementation automatically checks the status of the pointers and updates them accordingly. A DSP processor achieves this without using the other precious resources of the system. To read more about the analog device's hardware circular buffer, please goddamn my PDF. Summary. A digital signal processor is a specialized microprocessor for the kind of algorithms employed in DSP. An FIR filter involves data transfer, inequality evaluation, and a lot of math operations. Without a careful design, each of these operations can be a time-consuming process. The linear buffering is a simple but not at all efficient. Circular buffering is an efficient method of storing the input data of real-time system. Employing this technique, we need to perform only a single memory write operation for each new sample. Okay. Let's see the implementation then.
So here's the FIR filter header file, and I just want to go through it quickly, but we'll actually be filling in the initialization and the update functions of the filter together in just a second. So I'm including this standard int.h because I'll be using types such as uint8_t. After that, we are defining the filter length, and you can just set that to any value and then change the filter coefficients. I'm defining a struct which contains the circular buffer, the index for the circular buffer, and the current filter output. Then we have two functions. One is the initialization function, which takes the pointer to the struct, which essentially clears the buffer, clears the output, resets the index. Then we have the main function, which is the update function. So it takes the struct of the pointer, it takes a current input sample, and it returns the filtered output. Okay, so let's see how we can fill in that initialization and the update function. So here we are in the firfilter.c file. You see I've included the header file we just talked about, and the first thing we see is actually an array of the filter length, and that will contain our impulse response, and then we'll look at that later, how to compute the impulse response. Then of course we have the initialization function, and I've written that for you because it's kind of boring. All I'm doing is running through the buffer, the whole buffer length, and just setting everything to 0. then I'm resetting the buffer index, and I'm clearing the filter output. And you would do this when you create an instance of the object, and then you would pass that instance to this function, and that just clears everything for you.
Tamam.
Alright, so now comes the main function, and this is going to be I think the most interesting bit, and so let's do that together. So we have the FIR filter update function, which takes the FIR struct and the latest input sample and returns the latest filtered output. So I've written some comments here of what needs to be done, and let's fill this in together. So the first thing we need to do is actually store the latest input sample in our circular buffer. So we can do that by accessing the struct, and then we need to put it in place where our buffer index is. Right? So we store the latest input sample where our circular buffer index is pointing to in the circular buffer. Then of course we need to increment the buffer index, because the next time we store a new sample we don't want it to be in the same place. Of course this is a circular buffer, and we need to make sure that we stay within bounds. So we can't have a buffer index which is longer than the FIR filter itself. So that's what we're going to check for next. And if if the buffer index is equal to the filter length, then of course we want to reset it to 0, because the next time we'll increment it to 1. Okay, so now comes the most interesting part. This is where we actually do the filtering and we compute a new output sample. So the first thing we need to do is set the current output to 0 again, because we're going to be using this register, this variable, to actually store the latest output sample, and we want to start from 0. Now if you remember, this is the sum we need to implement. This is the actual convolution. So we can compute the latest output sample by following this. So essentially we need to cycle through the impulse response from 0 to the length of the impulse response and multiply it by the shifted samples of the input buffer of our circular buffer. Okay? So essentially all I'm doing now is implementing this sum. So let's do that. Of course I need some sort of variable to keep track of where I am in this sum, and I'll just call that a sum index. And we started off at the FIR buffer index. Okay, then we have a loop where we're looping through the entire impulse response, right? So all I'm doing is implementing that mathematical formula. Okay, so the first thing I have to do is check if the index is alright. So if the index is still positive, so greater than 0, I would like to decrement the index. So I'll do that. Now if it's 0, of course I can't decrement one further, then I actually need to shift the index. So now I've shifted the index, which we'll be using in this sum. Now I actually can get the impulse response and I can get the stored input sample from the circular buffer and then multiply them together and add it to the output. So I'm adding to the output the multiplication of the impulse response at my index n, and I'm timesing it with the input sample which was shifted. Okay, so to my output, which starts at 0, I'm adding the impulse response at n times by the shifted input sample. And again, all I'm doing is implementing this sum here. So the current output sample is the impulse response at an index times the circular buffer, which is the input buffer of a shifted index. This is all I'm implementing here. Okay, and that's pretty much all there is. This loop will run through, and after we've done with that, we have stored the filtered output in FIR out. So that's all we need to return. So all we had to do was store the latest sample, make sure we update the circular buffer index, then we compute the new output sample via convolution just by following this sum over here. And that's all this code is doing, and then we're returning the filtered output. And that's it. So now we can try and design a FIR filter and then test it out in real time. So as a global variable, I've made an FIR filter struct, and I've just called it low pass filter accelerometer. We're just going to be using it just as a demonstration to filter one axis of the inertial measurement unit's accelerometer. Then of course we have to initialize the FIR filter, essentially just resetting the circular buffer, indices, and the output, and we do that just by calling the FIR filter underscore init and passing the low pass filter accelerometer FIR filter struct by reference. So in a previous video on actually programming in STM32, I believe it was called STM32 firmware tutorial, we went through how we can actually write drivers for an accelerometer and gyroscope, and I would suggest you look at that video. I'll leave a link in the description. But essentially we had set up a DMA stream so that we can actually read the accelerometer data every time there's an interrupt, and this interrupt occurs 100 times per second, so at 100 Hertz, which is really good because we have a fixed sampling frequency, fixed sampling rate, and then we can always do our filtering as soon as we read something via DMA, and that's exactly what we're going to be doing here. So I have this callback every time the DMA stream reads a new sample, so 100 times per second. We read it, and once it's complete, we can then filter that accelerometer data, and so let's do that here. So this is actually where we would call the FIR filter update routine. So let me just type in FIR filter update. We pass the filter struct, and we pass the latest sample we read. So I'm just accessing this inertial measurement unit struct over here, which contains the accelerometer data. I'm just accessing the first value there, which is the x-axis. Okay, we would also like to transmit the raw and the filter data so we can plot the two and see if the filter is actually doing what it should be doing. And I'll just copy that over because it's not particularly exciting. You can see that in a previous video how that works. Essentially I'm just creating a buffer to store the text in. I'm printing essentially two floating points, the raw data and the FIR filter data, and then I'm transmitting it via USB full speed. So now that we have all of our filter code written, it's time to actually design an FIR filter, and we'll do it using this program I wrote. So we have this raw accelerometer data which will contain a lot of high frequency
Değerlerini mi alacaksın? Ne yapacaksın?
the array
Aynen bak. Bütün
with these
değerleri
filter
burada.
coefficients.
Gördün mü? Tamam.
And you can see here, this is the file it generates. So it'll tell you what the filter order was.
Bunu bir görelim bakalım ne yapıyormuş.
So now that we have all of our filter code written, it's time to actually design an FIR filter. And we'll do it using this program I wrote. So we have this raw accelerometer data which will contain a lot of high frequency components that we don't really want. We want the accelerometer to be essentially correct or valid for the long term. So we want low frequency data to remain and high frequency data to be filtered out. And the way we do that is via a low pass filter. So the first thing we do is in the bottom here we select the filter type, which is LP, which stands for low pass. We also said that we're sampling the accelerometer data at 100 Hertz, so we changed that here to 100. And filter length, essentially anything under 64 samples in filter length is probably fine, and the STM32 can handle it. But as soon as you go above that, it's going to have a real tough time keeping up. Just to be safe, I'm going to keep the filter length to 16 and shift it by 8 samples. So shift it exactly by half the filter length. So filter length, essentially you want to keep around 16 to 20. It's really hard to compute the filter for longer lengths. Now, we want the cutoff frequency, essentially, we want it less than 50 Hertz because that's a Nyquist limit. I'm going to put it something around 10 Hertz. So the cutoff frequency will be 10 Hertz. Anything below 10 Hertz should have a DC gain of about 1, and anything above that should be attenuated, is what I'm basically saying here. Now, first of all, let's leave the window function as rectangular, and rectangular means we're not applying any windowing. So click on Design Filter, and now you can see the filter response in the time domain. We can see the window function in the time domain, the filter in the frequency domain, and the window function in the frequency domain. As you can see here, we have these nasty side lobes because we aren't doing any windowing, and the filter response isn't too ideal, right? At about 10 Hertz, we only have about -6 or -5 dB of reduction. So the way we can improve that is by actually doing the windowing, what we talked about earlier, and a really good window to always use is pretty much the Hamming window is a pretty good window. So we click on Design Filter again. You can see our stop band attenuation is improved. We've reduced the amplitude of these ripples or these side lobes, and I think that should pretty much do us for now. So remember, sampling frequency, filter length, the amount of samples we shift, the cutoff frequency here, window function, and we want the filter type of low pass. Okay, so once we've done that, we can click on File, Export Filter Coefficients, and I'm just going to save it as a text file. There we go, and it says it has written it to a file. We can actually open it, and you can see here, this is the file it generates. So it'll tell you what the filter order was, the sampling frequency, and so on. And I've already made it so it converts it to a C array, and we just copy that over into our code, which is over here, and we just replace the array with these filter coefficients, and it's as easy as that. So now that we have all the filter coefficients and the filter code written, all that's left to do is essentially launch the program, upload it to the STM32, and we can do that by clicking this green arrow up here. Click on that, it'll then hopefully build, and then use via serial wire debug, upload it to the STM32 and the little brain board. This is a really cool program that I'll be using to visualize the website. I have the serial oscilloscope running, and the STM32 is logging data via USB. So the first column here is the raw data from the accelerometer x-axis, and the second column here is the filtered data via our FAR filter. And we can actually visualize this here. So I have the board in my one hand, and if I just rotate, and then we can see the values change. You can see the red curve is the raw data, so quite noisy, lots of high frequency noise. And the green curve is the filtered data. So I'm just doing very slow movements, and you can just see how the low frequency curve follows it very nicely, which is what we want. But all the high frequency data is kind of filtered out, which is pretty good. So if I just move it like that, you can see it follows it quite nicely. If I just let it stationary, another important point is that the DC gain is the same. So I'm not moving it, and we want the values to have the same mean, which they do, so that's good. But as you see, if I start increasing the frequency of oscillation, you can see that actually the green curve lags behind the red curve. So the filtered data lags behind the raw data. And this, of course, can be problematic. And this depends on your cutoff frequency and how much filtering you're applying. Because the more you filter the signal, the more delay you're going to introduce into the signal. And this is exactly what we're seeing here. So if I speed it up even more, you can see the high frequency information is really filtered out, which is what we set our filter to do. So it works really well up to the cutoff frequency, and as soon as we increase the frequency of the data, then of course we will lag and reduce the amplitude. But yeah, so this is a really nice visualization of our FIR filter actually working.
Woo! Cool video.
Responses.
Video. Bir şey öğrendim bu arada ben.
Typically then writing our own algorithms. If you haven't already, and we'd like to add the libraries to this project. In this video, I'd like example. We are going to be this as a demonstration platform along with the just audio analyzer filters. For example, the filters as they are so on, they don't suffer the same stability issues, but they do come at a price that they are rather expensive to compute. We are time to or it goes through the basics of FIR filters, the theory behind them, including convolution, frequency domain performances, and so on, as well as how to design FIR filters using the Windows sync method. And it also shows you a basic implementation just in C without the CMSys DSP libraries to get a basic understanding, so please do check those out beforehand. In terms of applications of FIR filters, make sure to check out video number 126 on my channel, which shows how to create a very basic impulse response loader to simulate, for example, the effects of a guitar cabinet and its frequency response, which we see plotted here, and also goes through a bit of the theory. Again, in this video, we'll be focusing on the CMSys DSP libraries, and I'll show you how to import them and how to use the FIR filter in the CMSys DSP libraries. As usual, a huge thank you to PCBWay for sponsoring this video. I had these digital guitar effects processor PCBs manufactured and assembled by PCBWay, and they did a fantastic job. For this, I used their PC.
Şimdi. Yapmadan önce. Yani bir boşalsın board'un içerisinde falan her yerde. Ben doktora da bir juvaramı tellendireceğim.
Ne kapatmıştım ben bunu ya? Yok. Ama yoruldum ya. Niye bilmiyorum. Çok yoruldum. Yoruldum. Bayağı bir şey okuyup öğrendim bu arada. Ne yapayım ben ya? Bakayım. Bitireceğim galiba çünkü yoruldum. Belki akşam gece yayın dışı devam ederim ya. Vallahi yordum. Yoruldum yani. Yaşa. Yaşa.